All right, people, the final unit. We just finished this, so this should be pretty um, fresh in your brain. But let's talk about sampling distributions and then get into some confidence intervals. So parameter versus statistic, right? Cut this in half. Parameter is a number that describes a population, right? The mean of the entire population we're interested in, the standard deviation, the true population proportion. We can also use P for that, right? A statistic is a number from a sample that I'll put in quotes, I don't know why, estimates the population parameter. Okay, so statistic we take from a sample. If we're trying to find what the mean is or get an idea of what the mean of a population is, we would find X bar. If we're looking for the standard deviation of the population, we'd find sample standard deviation, S of X, right? Or S sub X. If we're looking to find the true population proportion, we're going to take the sample proportion. Okay, all of these are sample blah, sample mean, sample standard deviation, sample proportion. Okay, they're samples because we got them from a sample, right? So those are called statistics. These are called parameters. Cool, cool. All right. When we do sampling distributions, we don't actually ever really do them, but we need to understand what they would do or look like in order to be able to make confidence intervals and do inference later on. So the idea is this. If I knew behind the scenes the true height of priority students, that would be the mean, right? But let's say I just randomly select 10 students at a time and find their heights. That would be a sample mean, right? If I plotted that, I might get something that's a little above. I do it again. I might get something a little below. I might get something right here. If I asked everybody in our classes, two classes, 40 of you went out and did samples, random samples, size 10 of the population, we would probably get something that would eventually start looking like this, right? We'd have some stuff that's a little wild. Maybe we get something really low. Oh my gosh, we got the whole basketball team in that sample, right? But it's going to kind of build up and it's going to look kind of normalish generally. And we'll talk about the shape and the spread and all that kind of stuff. But the idea is if we kept doing it, we would get a sample distribution, a distribution of our samples. We wouldn't do this in real life, but we need to understand what this would look like, right? And we need to understand how samples vary so that when we talk about a confidence interval and I find a sample and I create a confidence interval, I have an idea of how often it's good, right? Or how often it might capture this true population mean. Same thing with proportions, right? Proportion of prior students who have colds today. Let's say I could climb into everybody's bronchial tubes and find out what the true proportion is, right? And maybe it's like 20%. Right now I have a cold, right? So everybody's got colds right now. They seem to last forever, right? But if we did that, if we did the same thing, I asked all 40 of our AP Stat students, take a random sample of priority students, size of 10, and find what percent have colds, right? And we did that and we plotted everybody's results on here. Sometimes we would hit it dead on, right? Sometimes we'd be a little bit above, sometimes we'd be a little bit below, sometimes we'd be way below or way above, right? So we're going to have some sampling deviation. We're going to deviate from things a little bit here and there, but we'll probably end up something where most of it's centered on this. We call that an unbiased statistic, right? So that's the idea. And again, this helps us. We aren't going to do this in real life. We're not going to have 40 of you do this to figure out what the sampling distribution looks like. But understanding what the sampling distribution would be if we were to do one helps us understand things like confidence intervals. We take a sample proportion, we add and subtract a margin of error to it, and that lets us know if we captured the true population proportion or not, or we have an idea of how often that would capture the true population proportion. Cool? Cool. All right. Goal of sampling is to have an unbiased sample with small variance. So let's just give some X bars here. Our goal would be something that looked like this. This would be a great sampling distribution. Let's say let's just do 5. Um, versus if this is the true population mean, let's give the true mean there. What would this be over here if we had something like this? And this was all of our samples. All of our samples end up being over here, right? What would that be? This is biased, right? We don't like that. This is biased. How about this one? Here's the mean. Let's just say we're using the same scale, right? Same scale for all three. And I had something, well, like this, right? Again, we're centered around here, so it's unbiased, but it's got a larger variance, right? This is variance is high, right? Or standard deviation is high. The spread is higher than it is over here. So this is unbiased. This is unbiased. This one has a small variance. This one has a small variance, right? But this is unbiased with a small variance, right? So we would want this one, right? This would be the best choice, right? Makes sense. All right, sampling distribution of a sample proportion. The shape should get more normal, no, more normals, more normal as sample size goes up. We'll talk about that down here when we talk about nearly normal. The center of a sampling distribution, and this is where we could go. Anytime you see sampling distribution, you can come here. Second page, sampling distributions for means, sampling distributions for proportions right there. So this is a helpful thing to have. We're talking about proportions, so we're going to use this top one, right? My mean of the sampling distributions. So if I've added all these up and divided by the number of samples that we had, if we had 40 students conduct these, we divided by 40, we should get something pretty close to the population mean, right? And if we did this a gazillion times or all possible samples were collected, we would get this, right? So the center is the mean of our sample proportions is equal to the true population proportion. Okay. The spread, oh, sorry. Oh, yeah. No, we're good. We're good. We're good. The spread would be this right here, right? So the standard deviation of the sampling distributions of the population sorry, of these sample proportions would be equal to the square root of p times 1 minus p over n. Okay? And we could draw that over there. This would be the center, and one standard deviation would be this, right? If we're doing that. Cool, cool. Cool, cool. To use a normal approximation, we need to check two things. We'll eventually add randomness to this when we do confidence intervals, but independence and nearly normal are the two things we need to check for this. So independence, we check 10n is less than the population. And this is sample size. This is population size. A lot of you were using proportion here, right? 10n is less than 50% or something. It's like, what? No, this is the size of the population. We need at least 10 times sorry, we need at least, let's see, 10 times, um, 10 times sample size for the population. Okay, the whole idea behind this is we have a population to draw from. We can't be taking too much out because that's going to could change the nature of the population, right? We need that population to be big. We need our sample to be just a subset of it, and that subset can't be over 10%. Okay, nearly normal for proportions is NP, and N times 1 minus P need to be greater than or equal to 10. Okay, so this is our successes, and this is our failures. This helps ensure that the sampling distribution that we're using looks fairly normal. Okay, so what's nearly normal? The sampling distribution. Okay, population distribution may not be nearly normal, or the binomial distribution may not be very normal, but the sampling distribution, as the sample size increases, becomes more and more and more normal. Cool. All right, next page. All right, for sample means, same thing. We're now going to go to our green sheet, sample distributions for means. Here's the information that we're going to need right there. Make sure you can find it if you need it. The shape, even if it's not normal, even if this is the original population is severely skewed, the shape becomes more normal as the sample size goes up, right? We'll talk more about that here when we get to the nearly normal approximation. The center of all of those sample means, again, what we're doing is I sent 40 of you out to find the average height of priority students. You did 10 people each, right? These are all of our sample means. If we average those, where would that average be? Should be at the population mean, right? So this equals the population mean. And then the spread of these changes as sample size increases. As our sample size increases, we're squeezing in on things, right? So it looks like this for root n. Okay, so again, I could do this. That is there. This is one standard deviation. So that's there. Cool, cool. All right, conditions, independent, same as before. This is 10 and less than population, same as we did on the last one. For nearly normal for sampling distribution, um, is it stated? A lot of times they will say, assume that the population we're drawing from is fairly normal. If it is, then you're all good, right? Can you graph it or do they give you a graph, right? Does the graph look nearly normal? What we're looking for is symmetry, right? Does it look pretty symmetric? We don't want a skew. That's what we're commenting on. It looks nearly normal enough to continue on. It looks like not much skew. I don't know what word that is. Skew. Sorry. Right? There's not much skew. It's fairly symmetric. We can move on. If it's not stated, we don't have a graph, then we have to say n is greater than 30. Okay, and this gets to the central limit theorem, right? As sample size goes up, the sampling distribution for means becomes even more normal. Okay. So sample size goes up, sampling distribution for means becomes more and more normal. All right, let's jump into confidence intervals. This is the fun stuff. That's why we did all this stuff before in chapter 7. We jumped to chapter 8 and we got to do two different types of confidence intervals. There's going to be more coming, but for right now, we've got two of them that we can do. 1 second. All right, sorry about that. Confidence intervals. We have two different types, right? We have confidence interval for a mean and confidence interval for proportions. So our statistics will be the sample mean or the sample proportion. Okay, those are our two options right now for statistic. It's one or the other. It's either means or proportions. Critical value, if it's means, we're going to use a T star. If it's proportions, we're going to use a Z star. Okay, those are our critical values, and you should know where to find those, right? Going to table B and looking at the bottom, finding confidence level, whatever level we're looking for, and going up one, that's our Z star, right? For T stars, it's everything in here. We have to know the degrees of freedom, If it's, let's say, 23 degrees of freedom and I need 95% confidence, I go over and I look down and there we go. So that would be it for 23 degrees of freedom. So that would be our T star up there. So that's how we find those. Make sure you know how to do that. So those are our critical values. Um, so plus or minus times the standard deviation or standard error of the statistic. Okay, and we can find those again on our second page, right? Standard deviation is here, standard error is here. If we don't know the population proportion, we use the um, sample proportion, right? Or we could use 0.5 to be super conservative. If they don't give us anything, right? Use 0.5 for that. For means, it's right here. We take our sample standard deviation over square root of n. We usually won't have the population standard deviation. We will usually have this, right? So you're going to use standard error instead of standard deviation. Again, error is not a bad thing. It's just how much are we deviating? It's just another word for deviation. Okay, so this one is either so let's see, if it's means, it is sigma over root n or square root of p or p hat times 1 minus p or p hat over n. Cool, cool. Let's go. Ms. Lee wants to know, we're going to jump into a one proportion z interval. One prop z. Mr. Lee wants to know the true proportion of prior kids who can juggle. He asked 40 students and 22 of them reported they can juggle. So I'm going to write down P hat is 22 out of 40, and that is equal to, I think it's 55%. Okay, nice job, Priory. Create and interpret a 98% confidence interval for the true proportion of students who can juggle. All right, so we're going to check the conditions. Conditions are, we need randomness. So was some kind of randomness happening here? He asked a random sample. There it is. It was stated. Stated. Check. Boom. Next one. I need my rule for independence, which is 10 times my sample size is less than or equal to the population size. So there must be at least 400 Priory students. How are we on that one? Yep, we should be good. All right, let's do another one. Last one is nearly normal. Okay, so let's check nearly normal. That's NP. So 10 times, or sorry, 10, what's my N? My N is 40, my bad. 40 times 0.55 and 40 times 0.45. Both of those are greater than or equal to 10. So we have a nearly normal sampling distribution. We can proceed with the T interval. All right, name it, do it. So we're doing a one prop z int. I need to either say the name or the formula, and then I need to jump in and do it. Let's go. So let's go stat tests, find one prop z int. There we go. I've already done it. 22, boom, boom, and it's 98% confidence. So 0.98 and calculate, and there we go. So 3.367.733. That'll work. That's all I need to do. I don't have to do the formula. I can if I want to. You could do that P hat plus or minus Z star for 98%. I could figure that one out. Z star times standard error. That would be the formula for it. And then I could fill in, right? 0.55, find the Z star on my green sheet, right? And then use my square root of PQ over N and do it that way. I could do it. I don't need to though. All right, save some time, keep it simple, use your calculator, move on. Interpret this interval. Again, this should be memorized. We are blank percent confident, fill that one in, that the true, what are we talking about here? We're talking about a proportion. I think it was 98%, 98%. Proportion of Priory jugglers is between 0.367 and 0.733. You could say the true percentage is between 36.7% and 73.3%. That's fine. Memorize this, keep it simple, get it going. Follow-up question. Prairie School newspaper reported that over 75% of Prairie students can juggle, sorry. Based on the above interval, is there evidence of this? I would say there's not evidence. Evidence as 75% is above the upper bound of our interval. We have to compare this to our interval. Is it within the interval? Is it above the highest bound? Is it below the lowest bound? All of those are important considerations depending on the question of our interval. Okay. I could probably leave it right there, right? I might say, not evidence, 75 is above the upper bound, making it an inconceivable or unlikely outcome, right? I don't know, but that's fine. Interpret 98% confidence level. Level. This is the second thing to memorize, right? This one is in repeated sampling. 98 out of 100 confidence intervals would capture the true, this is an ad lib. What is it? Population proportion. I could leave it like that vague. I could probably put it in the context proportion of prairie jugglers. That would be fine, but this would be fine as well. Just in general, what does a 98% confidence level tell us? Means 98 out of 100 intervals capture the true population proportion. And that goes back to our picture from up here, right? If we created for each one of you who went out and found what proportion of prairie students have colds today, if you all created little confidence intervals based on what you got, most of you would capture, right? If we look at this one right here and gave it a margin of error, that one captures this. If we made this one, that one captures it. If you all had a little standard of error attached, how many of you within a margin of error would have caught it? Most of you. But this person over here wouldn't have caught it. Every once in a while, you have, if this isn't bias, this is just sampling variation. You're going to have a sample that overestimates the true parameter, right? And the confidence interval around that estimate is not going to actually capture it. It's going to happen, right? So that's what we're saying here, right? 98 out of 100 times, we catch it. We catch that true proportion within the bounds of our margin of error, right? Um, if we did it a whole bunch of times. Cool. Cool. All right. Let's go. Confidence interval for population mean. Miss Kippelman crochets beanies for Mr. R. Time to make each beanie varies, and the distribution of times can be considered somewhat normal. A random sample of 23 beanies took 15 minutes on average to complete with a standard deviation of 4 minutes. Okie dokie. Create a 90% confidence interval for the true time it takes Mrs. K to crochet a beanie. All right, so let's check our conditions. Do we have randomness? How are we for random? Yes, it was stated up above, right? Random sample. So we say stated, and we'll give it a little check mark. What's next? Well, what's next is independence, right? We need 10n is less than the population. Okay. So 230. So 23 is our sample size, right? 23 times 10. So we need at least 230 beanies crocheted. Crocheted? How do you do crocheted? I don't know. Is that right? We must assume that, right? I'll say yeah. If she's really good at it, right? She's made me a lot of beanies. It's nice. Random independence and then nearly normal. So for nearly normal, for this, we have to check three things. Number one, is it stated? Can be considered somewhat normal. So the distribution of times is somewhat normal. So it's stated up above. I don't have to do anything, right? I don't have to say n is, oh no, n is less than 23. I don't need to even need to say that, right? nearly normal population distribution, right? That's fine. All right, so let's name it, do it. This is a T interval. I can just say that. I'm going to grab my calculator. I'm going to go to stat. I'm going to go to tests. I'm going to go down to T interval right there. I'm going to put in statistics, and my X bar is 15. My standard deviation is 4. My sample size is 23, and I'm calculating a 90% interval. Let's see what we got. This is an older calculator. It takes a while. All right, there we go. 13.568 all the way to 16.432. Cool. And notice, I didn't write the formula. I don't have to. I either have to have the name or the formula. If you wanted to do the formula, that's fine, right? And then you'd have to have degrees of freedom and all that good stuff, right? This makes it so much easier. Just use your calculator, write the interval, move on. All right, now we interpret it. So we are 90% confident the true average time per beanie is between 13.57 and 16.43 minutes. Cool. Cool. All right, follow-up question. Crochet Magazine states that it takes a master crocheter 17 minutes to crochet a beanie. Based on your interval above, is there evidence that Miss Kippelman is a master crocheter? So I have to compare this to this. Okay, so what do we think? If it takes a master can do 17, and she's averaging between 13 and a half and 16 and a half minutes. I'd say Miss Kippelman is a master, right? Her time is less than the cutoff, right? I can't say that her time is. We are pretty confident that her time is. So 17 is above our upper bound on our confidence interval. I want to specifically talk about the confidence interval and the upper or lower bound, and is this in it or above it or below, right? Interval. Therefore, there's evidence she is a master crocheter. Perfect. There we go. That's it. Simple, simple. Keep it simple. Move on. How not to interpret a confidence interval. Okay, this is a typical, hey, which one is the correct way to figure it out, right? We're looking for 90 out of 100 confidence intervals created in the long run would successfully capture the true crochet time, right? That's what we're looking for. These are all wrong. Okay. There is not a 90% chance that the true time would be in the interval, right? 90% chance implies that it's variable, right? It is not variable, right? The true mean time is not a variable. It doesn't vary. It is set, right? So either it is, so 100%, or isn't 0% in the interval. Okay. 90% of sample times will fall in the interval. Remember, the interval you are creating is a sample, right? Comes from a sample. Our sample could vary very much from the actual, right? So we don't know where our sample came from, right? Again, we go back to this, right? We don't know where, if we just take one sample, we don't know how that compares to here, right? If this is the one, right, and I create a confidence interval on it, and my confidence interval goes this far, right? We're in the dark. We're 98% or 90% confident that the true proportion is somewhere between there, okay? But in reality, it's not, let's say, right? So we can't say 90% of sample times will fall in the interval. Is that true? Are 90% of the sample times within this interval? We can see that it's not, right? I get maybe 2 out of the 40 that I did here or something like that, right? So that can happen. Now, if we use this one, I would say yeah. So if our sample was right at the population mean, then I could say that. But we don't know where that sample is. It's a sample. It's got variability. Same thing with this one, right? 90% of all beanie crocheting times are in this interval. Really? If this is the mean, the distribution would look something like this, right? If it is unbiased, would 90% of the actual times be within this? No, right? No. Um, the time to make a beanie would be between blah and blah 90% of the time. Is that true? Again, let's look at a worst case scenario. If my sample was out here, right, would this capture 90% of the beanie times? No, right? So all of these are bad because they're assuming that our sample is like in line with the middle, right? And it's not. Our sample could fall anywhere, right? So let's this is proportions. Oh no, this is means, right? Right? This is means. Ours could be out here, and think about what that would mean. Yeah, see what I said mean? Right? Okay, cool. Hopefully that helps making sense. All right, sample size needed for a certain confidence percentage. All right, for proportions, if we don't know, if we don't have a sample proportion or they didn't say the population proportion should be around something percent, use 50%. Okay. And I think that's what we're going to do here. Mr. Lee wants to know the true percentage probably students can juggle. He wants his 98% confidence interval to have a margin of error of 5% or less. That would be this. How many students will need to be in a sample? Is this a problem? I think it's going to be a problem. All right. So if it's 98%, right? And this is a proportion, right? We're going to be using a Z star. So let's find that. Go to table B. This is where I actually do need to use it. 98% is 2326. So 2.326. All right. Margin of error is just going to be Z star times standard EV deviation or standard error. In this case, it'll be standard deviation. So margin of error, I want to be no more than 0.05. I want a Z star of 2.326, 2.326, and then I'm going to multiply it by the standard deviation. So that's root P, 1 minus P over N, and I don't know. That's what I'm trying to figure out. And they didn't give us a percent. Now, I could go back to that problem. I think it was 0.55, right? I could have used from before 0.55, which was the 22 out of 40, right? I could do that, but I'm not going to, right? I'm going to keep it conservative, go this way. All right. Math will happen. I divide both sides by 2.326. Then I square both sides. I end up with 0.25 over n. A little math happens, and I get n is equal to 0.25 over 0.05 over 2.326 squared. And then that equals, I figured it out before. See if I have it. Oh, I didn't want to type it in. I think it ends up being 541.0276. Now, ordinarily in real life, we would round that down to 541, but what do? Always up. Always round up. Okay. We're not even rounding up, right? If there's anything here at all, we round up 542 people. What's the problem? How many students will he need? He will need 542 students. What's the problem? That's more than the number of students we have, and that's more than 10% of the population, right? So we'd have a problem with our independence rule for sure. And we just we don't have enough people. All right. Means when we do sample size, we're going to roll over to a Z distribution, okay? Because we don't know the sample size. We're trying to find that out. And if you don't know the sample size, you don't know the degrees of freedom, so you can't use the T chart, right? We can't use this T because we won't know the degrees of freedom. So we're just going to estimate. We're going to use Z distribution. For this one, I think hers was 90%. So let's use, I don't think I stated in here, Let's use a confidence level of 0.9 confidence level, 90%. So Z star there, just so we can have a different one. 90%, 1.645. Some of these you're going to have memorized. Ooh, 1.645. That's one that you'll probably have memorized. That and the 95%, 1.96. You'll have that one done. Again, margin of error formula. Margin of error is equal to Z star times standard deviation. So let's do it. Margin of error we want within 1 minute. So 1 minute is equal to 2 point, oh, sorry, not 1.645 times the standard deviation is, her standard deviation was 4 minutes over the square root of n. This one's a little easier. We're going to divide both sides by 1.645. That equals 4 over root n. I'm looking like cross products, right? Remember that? Root n is equal to 4 times 1.645. Then I'm going to square both sides. N is equal to 4 times 1.645 squared. All right, let's do it. 4 times 1.645 raised to the second power, 43, and is equal to 43.2964. So what are we going to do there? Even though that's less than a 5, normally back in like fourth grade when you learn how to round, you would do it, but we're unlearning that. So we need 44 beanies to stay within that margin of error. Cool. Cool. That's it. People, we're done. Awesome. That's it. We'll see you in class.